Part B.2, compare growth functions. In B.1, we use two different methods to solve that element uniqueness problem. And we get two different solutions, right? In this one, we will compare which one is better. All right, so let's start, compare two growth functions. The concept of growth function given in part A. Dominant term, right? So let's recall a little bit dominant term. You get dominant term of the efficiency function first. After that, remove the coefficient part. Growth function, we don't look at the efficient part. Only look at the variable part. Coefficient part. All right. Which method is better? So let's look at this question first. The method one, the worst case efficiency, CW1 of n, this formula, 1/2 n times n minus 1. What is the growth function? So based on our definition, you can think about it. The second one, method 2, also the worst case, but this time, remember two parts. Checking part, n minus 1, but you need to pay the sorting part, right? Initial data organization, that work you need to pay. So you can see actually the amount of work for the data organization, that part is much larger than the checking part. But in any case, now let's look at the growth function first. The growth function for the CW1 n squared. Because we do not need to look at the coefficient 1/2. So we ignore that 1/2 coefficient. We have this n squared. Second one, n log n. The dominant term, coefficient just 1, so we still use that n log n. After that, the next round, we need to do the comparison. How to compare these two functions? Which one is faster? Which one is slower? For the long run, we want to look at when n is very large. We want to look at that training behavior. All right. Use ratio to compare two growth functions. Ratio. Okay. So that's the commonly used method. So we use the limit, because when n goes to infinity, we want to calculate the limit of the ratio of two growth functions. After cancellation, n limit of n over log n when n goes to infinity. How to calculate this limit? You need to have some calculus background. So let me do that part. Just recall your calculus background a little bit. First, the log n, here we didn't put the log base here. Actually, we can assume a general log base a, but we need a greater than 1. In that case, log base a of n, it is a positive function. Otherwise, if a is between 0 and 1, so that log base A of n is negative, less than 0. So we don't want to look at the negative function. So that's why we assume A greater than 1. All right. Then, how to see this limit equals infinity? How to see it? Yeah. Here, I try to use two different methods. Two different methods we can see the answer. The first one, yeah, we do variable substitution. Yeah. Because the log function, we feel we're not quite familiar with log function, so we want to do some substitution. Yeah. We let another variable u equals log base A of n. Okay. U, new variable. If we introduce a new variable u that equals this whole log function. After that, based on the definition of log function, we can write n equals a to the u power. A to the u power of u. Yeah. Yeah. All right. Then, limit of the ratio can be written. This time we use u variable. U still goes to infinity. This time, numerator a to the u and denominator just a u. All right. When we write in this ratio, we can say it is infinity. Why? Here we use one fact, famous fact. Okay, yeah. An exponential function, a to the u, that's exponential function. But this exponential function, the base is greater than 1. Otherwise, it will be different. An exponential function with base greater than 1 dominates any polynomial. That is the, commonly used fact. Why? We can prove it. Why? We can prove it. Okay, yeah. All right. And the denominator u, it is a polynomial. It is a linear polynomial. Very simple polynomial. Yeah. If we want to know why, our method 2, we can prove it. In our method 2, we will use calculus to prove it. Yeah. All right. How to use calculus to prove it? Yeah. Here, let me recall, we need to use L'Hopital's rule. Some of you may have heard of this. L'Hopital's rule, yeah. In calculus, Calc 2, actually, Calc 2, you will learn, you probably, yeah. So some of you have that background, you know it, yeah. But some of you may not know it, yeah. So you need to study a little bit, yeah. So method 2, we use L'Hopital's rule to calculate the limits. Here, let me show you the whole procedure. So you'll try your best to understand it. Yeah. All right. Limit of ratio of two functions. All right. When we calculate limit of ratio of two functions, you may have a chance to apply L'Hopital's rule, but the condition should be right. You need to make sure the condition is right. Then you can apply L'Hopital's rule. Otherwise, you get a wrong result. So what kind of condition? First, the limit of the ratio should be a special form. Should be a special form, okay? Limit the ratio of, when it is satisfied that special form, then you can use the limit of ratio of two derivatives. Limit of ratio of two original functions, when you try to find it, you can calculate limit of the ratio of their two corresponding derivatives. That's a powerful method using derivatives. Yeah. What kind of condition, what kind of right form? Here we call indeterminate form. The ratio should be indeterminate form. So what's that indeterminate form? The first one, infinity over infinity. What do you mean infinity of infinity? So this is the form, okay? Yeah. Do not try to, think about, so what is the number infinity over infinity? Indeterminate. It could be any number. It cannot be determined, so we call it indeterminate form. Okay? So that means when n goes to infinity, the numerator will go to infinity and denominator will also go to infinity. So that's what we mean here. Yeah. So we just call it indeterminate form. Another special case, 0 over 0. Do not try to calculate, so what's the number 0 over 0? Here we represent some special form. So what is that form? When n goes to infinity, the numerator function goes to 0, and denominator function also goes to 0. So that's what we mean. The limits 0 or infinity. All right? Yeah. You can see here we have the infinity over infinity case. Yeah. So let's take a look. All right. A to the u over u, numerator goes to infinity, right? Denominator also goes to infinity. Yeah, so that's the indeterminate form. So we can apply L'Hopital's rule. When we apply the L'Hopital's rule, we need to take derivatives for the numerator and denominator respectively. So let's take a look. Yeah. So this, we check the form is correct, so we can apply L'Hopital's rule. Otherwise, you cannot apply. It will be wrong. If it's not infinity over infinity or determinate form, later I will show you some example so you can see it. Yeah, later. Yeah. All right. So now we just apply L'Hopital's rule right here. Derivative of the numerator. Yeah. So you can find the formula. You do not need to memorize it. You can easily find the derivative of that a to the u, that function. Natural log of a, natural log of a first times that function again, a to the u. That's simple. You only need to multiply original function by that log, natural log of base number a. That's it. Now, denominator u, derivative just a 1. You know it? So that's easy. Power rule. Yeah, power rule. Yeah. U, derivative 1. Yeah. All right, so now, what is the limit of this one? That's easy. Yeah. Because denominator is 1, so then we just look at the numerator. The numerator, when u goes to infinity, it is infinity. So the whole ratio, the original ratio is infinity. Yeah. Here, remember, we have this a greater than 1 condition. Yeah. Because a greater than 1 condition, it is important to tell the numerator goes to infinity. Yeah. All right. Here, there is one thing I want to point it out. Yeah. One thing I need to point it out. So what's that? Yeah. Because when you take derivatives, on some functions, you need to make sure the functions use continuous variables, not discrete variables, continuous variables, not discrete variables. If discrete variable, you cannot take derivative. It does not make sense. Now, why is that? Let me explain the reason behind it. Why you have to make sure the functions that you take derivatives must use continuous variables. Here, let me use this example, related example. Here, we do not do substitution. Let's just calculate limit of n over log n directly. Yeah, we can do it. Yeah. The reason is simple. The reason we can use L'Hopital's rule to calculate that limit directly. So we do not need to do substitution. Yeah. So another way to find its limit. Yeah. All right. But here, there is one special thing you should be very careful. That is, and here it's a discrete variable. Why discrete variable? Because it only takes integer number 1, 2, 3, and so on. Discrete variables, derivative of the function not defined. It does not define. You cannot apply derivative on it. Conceptually, it is wrong. Conceptually, it is wrong. But some people still do it. Some people don't worry about that. So they just apply it anyway. And finally, they get so-called correct result, but not quite right, not rigorous math. Here, when you read a textbook, you should be careful. That in our textbook, it applied derivative on this function directly, not changing to continuous variables. So it's not a rigorous math. So here, I want to correct it in this way. So this time we continue another ratio using continuous variable x. This time, x takes continuous values. So what's the continuous value? I think you know it, right? Yeah. From 0, 1, 2, but your x can take all possible values. No gap. Continuous way to have all the positive values. Yeah. Okay? All possible values. So continuous variable. In this case, then, because it is an infinity over infinity form, so we can apply L'Hopital's rule. When we apply L'Hopital's rule, we take derivatives, x derivative 1 log base a of x derivative this expression 1 over natural log of a times x. Okay. Then we do simplification. This expression, because natural log of a greater than 0, right? Positive. A greater than 1, so it's positive. A positive number times x. The variable goes to infinity. It is infinity. After we get this ratio, when x goes to infinity, it is infinity, then we come back to the original. When we come back, because x can take all the possible positive values, how about we just take integer values? we just take the special integer values. That's still correct, right? Still correct. So that's why we conclude limit of n over log n is also infinity. That is the rigorous way to get a conclusion. Rigorous way. Yeah. So we replace the original limit by a closely related but using continuous variable. Then we can apply the L'Hopital's rule, taking derivatives, get the answer, and finally we go back to the original limit. Then we have no problem. Okay. All right. Conclusion. Yeah. At the end, we have this conclusion. The algorithm with growth function n log n is faster than the first method with growth function n squared. That means second method is better. So when we pay investment to organize our data, we can get a better result for this particular problem. All right, so we finish our video B.2.